All right, so I'm glad to share some of our recent research to accelerate large language model and the visual language model on the edge devices, which is crucial for designing agents. Since lots of agents, you want to run them on the edge device. You don't want to send your data to the cloud, but running things on the edge is very challenging. So what we work on is basically make neural nets much smaller and faster to run, more resource efficient, such that you can run them on edge devices. This is some of my previous work in this direction, including deep compression, which can reduce the model size by pruning and quantization, and also the efficient inference engine, which can directly run inference on the sparse and compressed neural network. So in the context of smart AI agents, this kind of pruning and quantization approach is actually very crucial, as well as designing models that are fast and small to run to begin with. So let's start with the visual language model, which is a critical component to understand the world and also making actions. So let's talk about the new architectures for visual understanding and how to deploy them on the edge. I will cover 3 pieces of work for understanding, and if we have time, we can cover one more for joint understanding and generation. So let's start with VLA, visual language model. So to build those smart agents, you want to understand not only the text, but also the image, even the videos. So this is the visual language model we built that's deployable on the edge device. You can just saw it on the Jetson running on the Jetson RE Nano. We can ask what is the unusual about this scene, any safety concern, and the VLA visual language model can tell you this is a dangerous activity, somebody is hanging in the air, etc. Okay, so VLA provides an efficient recipe from data curation to training all the way to deployment for the visual language models, even deployable on the laptops. It's trained with interleaved image text. Pre-training enable this in-context learning capability. And it's all fully open sourced, including the whole training pipeline. So here are some examples of in-context learning capability of VLA. So you can tell how much do I have to pay for the beer on the table. With the reasoning capability, it can tell you it's $6 by 2, since there are two bottles of beer. So altogether, it will go to see the menu and do the OCR to find the price for unit price, and then times 2 to get the total price. On driver scenarios, we can ask different questions, like if the driver is distracted, VLA can tell you it's distracted. Is the driver on the phone? Yes, the driver is on the phone. How many people are in the car? There are 2 people in the car. One is here, one is here, although this guy is pretty small. And the interesting thing is VLA is deployable on the edge device. So this is showing VLA deployed on the MacBook. This is MacBook Pro, MacBook M1 running on the CPU. We can ask what is the image. It can tell you this is Mona Lisa. And we ask who drew this, is Leonardo da Vinci, etc. And such on-device deployment is enabled by a quantization technique that we developed called AWQ. Okay, so AWQ is a on-device large language model and visual language model compression technique. It's called activation-aware weight quantization for LLM and VLM. The goal is to deploy VLM and LLM on device on the edge, such as Jetson Orin, this AI PC. The challenge is that for a single batch inference, the weight memory is usually the bottleneck. Okay, especially at a low batch size, you cannot fit the memory, making the LU idle. So we want to quantize the weight to only 4 bits, using 4-bit weight, 16-bit activation, and 16-bit arithmetic. But naively quantizing it to 4-bit is very challenging. You have only 16 different values. Okay? And we find traditional methods, when you are quantizing the weight, you just look at the weight. That's not enough. Instead, we should look at the activation that the model is operating on. So we call it activation awareness. Okay? Activation awareness to preserve the salient weight channel by scaling according to the activations. In particular, if an activation channel is big, then we have to scale up the corresponding weight channel. The intuition is that if you scale it by 2, you are effectively adding 1 more bit, assuming other weights stay the same. If you are scaling by 4, you are effectively adding 2 more bits. So in this way, we can deploy the 7 billion and 13 billion parameter model on a edge device. This is the tiny chat computer that we built. It has a Jetson Orin Nano, which has only 8 GB of memory. We can run a 7 billion parameter locally on device. You can see in the back, it's actually pretty tiny device. You can fit this in a battery constrained scenario. You don't need to send anything to the cloud and fully running things in the local. And if you see the acceleration result, actually with the quantization versus without quantization, we can achieve about 3x speed up measured on the Jetson Orin Nano, Jetson Orin mobile GPU in this case. And AWQ is actually widely available these days. For example, it's available at NVIDIA TensorRT LLM. And also it can fit not only on the edge, but also for the cloud, you can fit a 180 billion parameter, 180 billion parameter model on a single H200 GPU. And here are some adoption in industry. Okay, now let's come back to the visual language model. So we aim for continually building small and compact models that can run efficiently, for example, for building agents. So how do we further make it more efficient, right? So we explore one technique, which is using quantization, okay, reducing the weight. But a big bottleneck when we are switching from image to high resolution image, from image to video, is the number of tokens. Okay, there are so many tokens. But it's very important to use more tokens because the spatial and temporal resolution helps a lot on the accuracy. Okay, so we want to scale them up. First, scale up the tokens using more tiles, videos using more frames, and then compress the tokens. Okay, doing spatial token compression and temporal token compression. So this is one interesting idea. And the other idea we used in the second version of VLA, which is called NVLA, include the dataset pruning. This is for training efficiency. We want to filter out the examples that are either too easy or too hard based on the response from a small and a large model. We also applied the FP8 training for both the weights and activations to reduce the peak memory usage. So for example, we are using this technique called code quantization approach for 8-bit training for the VLA visual language model. So how do we do 8-bit training, FP8 training? So this is the acceleration. Basically, we can reduce the memory consumption. Previously, it's 65 gigabytes all the way to only 42 gigabytes by using FP8 training compared with BF16. And this is even better than the transformer engine, which is about 62 gigabytes. So what we find during FP8 training is that we want to use per block quantization. Once we use per block, per group quantization, the FP8 dynamic range we find is heavily underutilized. So this is the full dynamic range on the left from the top to the bottom. But if you observe the first order momentum and the second order momentum, actually they are using only half or even less, especially the blue part, the second order momentum, maybe 1/10 of the total dynamic range. Some outliers is occupying the whole dynamic range. It's like you have a giraffe in the room and everybody becomes ant and become dwarfed. So you're not fully utilizing the dynamic range. And if you use the same ruler to measure the giraffe and to measure the ant, of course, the ant will be dwarfed. So we want to align the dynamic range during per group quantization. And the idea is actually quite interesting. rather than quantizing x could be the activation or could be the weight, we quantize x to the power of k. Okay, we preserve the sign and we quantize x to the power of k. Okay, so a large k will lead to a larger expanding capability to expand the dynamic range. For example, originally the dynamic range is 4. If you quantize x to the power of 2, the dynamic range becomes 16. If you quantize x to the power of 3, it becomes quantizing the dynamic, we have the dynamic range of 64. So each quantization group share the same k. And we want to decide the k during the runtime, and we write fast kernels to minimize the overhead by kernel fusion. And as a result, this is the original. The red part is the first order momentum. The blue part is the second order momentum. The shallow red is before the expansion, and the solid red is after the expansion. You can see after the expansion, you can better utilize the dynamic range. Okay, and another idea is we find those nonlinear layer actually consumes much more memory compared with these activation layers. So we want to mix granularity, use different granularity to balance between the precision and the speed up. So this is the actual units of memory we consume actually using code. We quantize not only the attention layer, but also those nonlinear layers. They actually occupy a pretty large portion of the total memory consumption. And here are the results. The convergence is very well for both language model and also visual language models. We tested all the way to 300 billion tokens, and about this is the speed up and also the memory consumption reduction. So for example, using code, which is red, you can get roughly, depending on the number of GPUs, using 2 GPUs, you can almost get 2x speed up. 1 GPU previously, old methods cannot fit, now you can fit. This is the memory consumption. You get about 1.x reduction in the memory consumption. 4 GPUs, 8 GPUs. In 1 or 2 GPUs, previously cannot even fit the training in 1 GPU, but now with code, FP8 training, you can fit. Okay, so we go back, dataset pruning, FP8 training, and then during fine-tuning, we adopt the efficiency technique in LoRa and QLoRa. We find the learning rate actually should be set differently for the main branch, for the visual encoder, and also the language model when you're using LoRa and QLoRa. Okay, so the visual encoder and LLM should use different learning rates. And we find sometimes just tuning the normalization layer can help a lot. You don't even need to tune the full model. And finally, we did apply the quantization like before, where we quantize the visual encoder with W8A8 and quantize the language model using W4A16. So visual language model, 8-bit weight, 8-bit activation since it's compute bounded. Language model, 4-bit weight, 16-bit activation since it's memory bounded. And by applying a lot of such efficiency technique, you can still well preserve the accuracy. Okay, so this is on par or similar accuracy as other models in the video and image benchmark, but can deliver a lot of speed up using the above efficiency technique. For example, the training time measured in GPU days decreased from 800 GPU days to 80 GPU days, primarily thanks to the dataset pruning technique. Okay, if it is too easy or too hard, we just prune them away. So this is the image. For video, we can reduce the training time from 400 GPU days to 200. And this is speed up for the pre-feeding latency due to token compression, due to quantization. We can reduce the TTFT from 55 to 35 milliseconds for image, more than 1,400 milliseconds to 600 milliseconds for video. And this is the increase of the decoding speed. Especially for videos, it can increase from 50 to 150 almost. Okay, so this is the VLA visual language model. So recently, we continue to work on this topic to scale up in two aspects. One, we want to scale up to long video understanding. And second, we want to enable the reasoning capability to do more useful stuff, especially for agents. You want to do a lot of reasoning depending on what you are doing in the past to give very insightful actions in the future. So recently we introduced this long VLA R1, which is a full stack framework, training inference model design dataset, full stack framework for long video reasoning of VLMs, including a large scale dataset we introduced in this work, and also a COT plus SFT, and also the RL training pipeline. Okay, first using COT SFT and then using RL. Also, we provide an efficient multimodal reasoning sequence parallel training infrastructure. So how to efficiently train such reasoning models, given that the sequence is usually pretty long when you are doing the rollout. The sequence is pretty long since you want to do the reflection. Okay, you think about it for a while, generate some results, and then reflect in the past, and then generate more responses. So the sequence generated is usually pretty long, and you have many rollouts. Okay, so one GPU cannot fit, so you need more GPUs, even more machines. So this sequence parallel infrastructure is very crucial. So this is the overall training pipeline. We started with a VLA visual language model. It's open source. We first do the context extension using the long video SFT data, okay, with the multimodal sequence parallel, which we introduced in the long VLA paper. It was appeared at Acquire earlier this year. So we extended from VLA to long VLA, okay, by using a long video data set using SFT. Now you have long video understanding capability with context extension. Later, if I have time, we'll talk about long context techniques and KV cache pooling technique to make it more efficient. So that's in the long VLA paper. In this paper, we want to do one more step from long VLA to long VLA reasoning. Okay, so it has two steps. The first step is to do the long chain of thought SFT. Okay, that's the stage one. This is still using the multimodal sequence parallel. Okay, this is the reasoning warm-up. So you want to give it a lot of hand-holding to do SFT to enable the COT capability. And then we do the long video RL, okay, using the multimodal reasoning sequence parallel, okay, to scale up the reasoning. So this part is further expanded on the bottom. We have actually 4 models here. You can see we have a policy, the long VLA model, which is frozen to give the policy, and then we want to have a reference model which is frozen, and also a model under training, which is right here, and we do the rollout for different sequences. So these are the generated results. Okay, we collect the reward right here, and then we have to actually do the pre-fitting again to get the logics. Okay, so these are the logics. And in here, sequence parallel is very crucial because we have to do a very long unrolling, and we have to do a lot of sharing because the prompt and the video a lot of things we want to share as much as possible during the training process. So this is the workflow of a multimodal reinforcement learning sequence parallel. So it has 4 stages. The first stage, we want to shard the video frames across multiple GPUs, okay, feeding the videos and also the system prompt, and as well as the question. And stage 2 is the recycling the video embeddings. You have multiple visual embeddings to do the GRPO rollout across multiple GPUs. And this is using the VLM engine. Okay, another challenge point is the training and inference actually are using different infrastructure. Okay, so for inference, we want to do in the inference framework, which is VLM, and for the instead of the training infra, which is not quite efficient just for training. And in the stage 3, we want to shard the tokens to balance their own workload. We first gather the global input embedding and then pad the sequence and then shard to local GPUs. And finally, in the stage 4, we do the LLM pre-feeding. So this is the result. Performance on video sending benchmarks. We can compare the long villa versus the long villa R1, the same model size, but using this reasoning training infra, we can actually have significant speed improvement for the accuracy. This is with subtitle about 2-point increase, with subtitle about 3-point increase on the accuracy. It's pretty clear improvement on top of long villa across both the video MME and RL benchmark, showing that actually this training infra, the training data set, this training flow is actually quite effective. And above is comparing with other baselines. And we can see by using the MR sequence parallelism, okay, the multimodal reinforcement learning sequence parallelism, we can drastically decrease the training time. Okay, as we are increasing the training frames, the acceleration is more and more apparent. For example, with 256 training frames, with the MR sequence parallelism, we can achieve almost 9x speed up, so that you can train on longer frames. Okay, longer frames is very helpful because the more frames you use, accuracy will also go higher. And it will plateau roughly around 256 frames. Okay, so that's why we want to have the 256 frames on the top right corner, and also to accelerate it by 10x, 9x, such that the training cost is as if you are training on only 16 to 32 frames. But the accuracy on the bottom right, the 256 frames is a lot better than the 32 frame. And you can see the long villa R1 is much better than the long villa without the reasoning capability. And we categorized the task into temporal task, goal, plot, spatial, and overall. So such categories. And compared with GPT-4o, Gemini, video R1, and long villa R1. Actually, this quick model is actually quite competitive on these benchmarks. Okay, let's see some examples. This is a football game, 2022 FIFA between Argentina and the Netherlands. The question is, you are shown a 30-minute, it's pretty long, it's 30-minute video segment, actually a video segment, sorry, from a football game. The score remains 2-2 throughout this period and no goal accessed. This is another example for playing Texas Hold'em. Since the topic is AI agent, we wish in the future people can leverage this to build an AI agent and go to Las Vegas. That'll be fun. So the question is, this guy wearing sunglasses and maybe blue shirt, and this guy wearing a black jacket, playing Texas Hold'em, and this guy holds the ace of clubs and the king of hearts. Well, this guy, cards remain unknown. The community cards are as follows: 7 of clubs, jack of hearts, 2 of hearts, diamonds, river, king diamonds. Based on the betting pattern observed, assume you are this guy, you are Thomas, and know that your best possible hand is a pair of kings. After analyzing the video, infer this guy's hand. There's 4 choices. Okay, and let's see the reasoning process. On the top, his check call of 90,000 C bets implies a decent equity, possibly a top pair, a draw, or a strong second best hand. a monster would likely raise to deny equity, while weak or missed hands would fold. The turn brings more draws, further checks again, likely controlling the pot with top pair or similar. Thomas' check back reinforces this line. Hands like 3, 10, or weak jacks are unlikely due to the pre-flop and post-flop passivity. Premiums like AA or KK would probably have been 4-bet. The line best fits KJ, top pair, strong kicker, and flexibly to respond to the river. So the answer they give is the A, club king, club jack. And there's another example when we are moving the boxes. Let's watch the video as the last demonstration. So there are several cups, and there is several boxes, and there is a ball. There are 3 boxes. A purple ball initially placed in the middle box. The positions of boxes are swapped. Please analyze the step-by-step movement trajectory of the box containing the ball through the video and determine the final position of the ball. Okay. Since the left box is now in the middle position, the ball which was previously in the middle box is now in the left box. Swapping continues with boxes rotating left, but the ball's position does not change because it's always in the left box. So I give the answer A to be left. And actually, this is only possible, the reasoning is only possible with large enough frames. For example, we tested 8 frames all the way to 64 frames. It all failed because you do not have enough sampling to miss some of the critical trajectory in the middle, then you're going to fail. Okay, that's why we call it, we want to emphasize on long VLAN, R1. So reasoning really acquire many frames, like 256 frames in this case. Pretty much on time. Okay. All right. So these are the visual language model demos. How to further make the long context more efficient. I don't have time to cover in this presentation, but feel free to check out this work for long context and sparse attention for long video tasks like streaming LLM, dual attention quest, serve, and sparse attention. Okay, that's all for my present today. We talk about VLAN and VLAN, long VLAN reasoning to deal with the long reasoning tasks on videos. Okay, thank you.